So a couple of things. Good morning, everybody. One thing is that the exam 2 review is now up. I've got it going and is up on my Google site. And so don't hesitate to get into that review and start working on it. So this is...
Wait, you mean exam 3?
Oh. So exam 3, let me repeat, thank you, Janessa, for pointing that out, yes.
You're welcome.
So exam 3 review is up on my Google site. And so that's a very lengthy review. There's lots of problems on it. It'll be longer than the test, but it's a very good review. All the answers, all the solutions to the problems are up also with that review. And so please start taking advantage of that exam 3 review. If you work hard on that review, if you can do that review without a lot of outside help, if most of the problems on there are things that you can do, then you're going to do well on the test. Remember that the testing window for exam 3 is November 30th through December the 5th. I will be on campus November 29th and and November the 30th. I'm sorry, November 29th and November the 30th. So if you are having any questions, then and you want to come and talk to me in person, that would be a good time to do that. My online office hours, I remind you of these every lecture. So remember that I have online office hours for you guys 2 times today. One thing I do want to point out is that I'll probably be running a little bit late for office hours this evening. And so it'll probably not be until about 8:15 that I'm online. So be patient and remember, just keep that in mind. And then I have hours tomorrow and Sunday and Monday. The factoring contest, let me point this out to everybody. I did send an email out to everybody about the factoring contest. And I see that Sandra in particular has said that she would love to do it, but she can't take the time off for it, which is unfortunately nothing I can do about that at this point. I'm not running the factoring contest for the first time ever. We've been running it for probably 8 or 9 years now. The math club, Aftermath, runs the factoring contest. So it's tomorrow, and it is in Winship 207 at 3:30, and I have posted a review for that. I have posted a review for that on my Google site, and so it's a pretty lengthy and pretty thorough review of factoring. And so that's a good, and it's where your other exam reviews are also. I do offer some extra credit for my students who participate. I will get a list of students that participate in the factoring contest. And so if you go and you do participate, and then I'll give you some extra points on exam 3. So hopefully I can get a couple of you interested in that. I know some of you who are here with me live today, and then some of you who are going to watch this video later are pretty good factors. And so there's definitely some of you who would be pretty good at it. But it doesn't matter. Don't think that you can't participate if you're not not making a 100 average on the test or anything like that. We have students who are just typical old intermediate in college algebra and 0308 students go and participate and do well in the factoring contest. There are actually cash prizes for the top 5 places also. So, that would be a good thing for you to participate in. It's kind of fun. There's going to be some free food there. And there's nothing that bad could happen. The worst that could happen is you go and you spend 45 minutes or so at the factoring contest, and you just get extra points on your exam 3, and that's the worst that could happen. The best that could happen is that you actually get a cash prize at the same time. So, anybody have anybody who's online with me right now have a question about the factoring contest?
No, I'm gonna go.
You're gonna go? That would be great. If you go, I would bring a student ID with you just to make sure. They're going to check your ID because they want to make sure that you're in a math, either you have to be in math 0308, 0310, or college algebra. So I'd love for as many of my students to go as possible, and it's a good way. That's a good way to get a few extra points, and you do some practicing with factoring also. And there's nothing, like I said, negative about that at all. So if there are no other questions, then today, and I guess there aren't, from those of you who are with me live, then today we are going to cover linear inequalities in two variables. Linear inequalities in two variables. What we have been talking about are linear equations in two variables. And so now we're going to talk about linear inequalities. So I have some setup, some stuff that I need to talk about here, and a little bit of reviewing also. You know, we've been doing a lot of stuff with lines, and so let me remind you that an equation like this, ax plus by equals c, this is a linear equation in two variables. And what do we know about this, the graph for this kind of equation? We know that the graph is always a line. And we've spent a fair amount of time talking about how to graph the different ways. There's not just one way, but different ways of graphing linear equations in two variables, right? Let me emphasize again that this is an equation in two variables. Linear equation in two variables. So we have talked about, well, so today what we're going to do is we're going to talk about linear inequalities in two variables. And so linear inequalities in two variables are statements that look like this. Ax plus by less than or equal to c, ax plus by less than c, ax plus by greater than or equal to c, and ax plus by greater than c. And these are what we call linear inequalities in two variables. All right, so I want to make sure that you know as algebra students what you're talking about and the difference between an equation and an inequality. Right, an inequality has an order symbol that's part of the statement, right? So you've got these less than or equal to, less than, greater than or equal to, or greater than, whereas an equation has an equal statement in it, an equal sign in it. Right, so it's a different beast in a lot of ways as far as what we're looking at here. Now, in order to be able to deal with a linear inequality in two variables, you have to know something about linear equations in two variables. And so I do want to go back and review graphing. Let's just real quick here and review the different ways to graph a linear equation in two variables. Because we've talked about several different ways, and we want fairly efficient ways to do this. So let's go back and do that for a minute. So for example, if we have 5x minus 3y is equal to 6, right? One way that we've talked about that's a nice way of graphing an equation like this is to use intercepts, right? Use x and y intercepts. And remember, the way we wrote that out is we made a little t-table, but a very short t-table, and we specifically looked for the x-intercept and the y-intercept. And remember, the x-intercept is when you put 0 in for y, and the y-intercept is when you put 0 in for x. So you make the short little t-table, and you just plot the intercepts. So when you do that, when you put a 0 in for y, right, you always get equations that are easy to solve when you do this, because 3 times 0 is 0. So you end up with 5x equals 6, or x equals 6/5. So you have 6/5 right there, so 6/5, 0. Don't forget that 6/5 is 1 and 1/5, right? Because you divide 5 into 6 and it goes once with a remainder of 1. All right, and then when you do the y-intercept, you put in 0 for x. And so you get negative 3y equals 6, or y equals negative 2. So you have a y-intercept at 0, negative 2. And then you just plot those two intercepts, and you've got a decent sketch of the line. No big deal. So 6/5, 0, 1 1/5 is about right there, and 0, negative 2 is about right there, and there's our graph. All right, so that's one way that we've talked about for graphing is by using intercepts. Another way that we've talked about for graphing lines, so like, for example, if you have the equation in this form, y equals 3/4 x minus 3, let's say, right, that equation happens to be in slope-intercept form. So here, it was probably easier to graph this by using the slope and the y-intercept, and using the slope to sketch the graph. So remember, we've talked about doing that. So in this particular problem, because that's in slope-intercept form, we know that the slope of this line is 3/4, and remember, that's the rise over the run. And then the y-intercept is at the point 0, negative 3, right, because of that negative 3 in the equation there and where it's located. So you get a y-intercept down here at 0, negative 3, and then you use the fact that the rise over the run is 3/4, and you take advantage of that. So you go up 3, just counting, and then over 4. Right, so you go up 3 and over 4, and you get another point on the graph that way, and there's your graph. A pretty efficient way of sketching the graph is by using, if you get the slope, and if you have a point, using a slope and a point, it's an easy way to sketch the graph of a line. All right, so if those are things you can identify quickly about a line, that's an easy way to graph. We've also talked about equations like this. So, for example, we have 2x minus 5y equals 0. The problem with that equation is that the x and y intercept passes through the origin, right? The x and y intercept are the same point, 0, 0. And so in a problem like this, it might not be a bad idea to actually put it in slope-intercept form, solve it for y. So you have negative 5y equals negative 2x. Just subtract 2x from both sides and divide by negative 5, and you have y equals 2/5 x. All right, so when you get y equals 2/5 x, what do you get there? You get that the slope is 2/5. And so that's a nice, easy way of graphing the line. You know that it goes through 0, 0. So it passes through 0, 0, and then the rise over the run is 2 over 5. So you go up 2, and then you go over 5. So I think it's important that a college algebra student, you guys are not far from being college algebra students, probably. I mean, most of you, that's the class that you're going to end up taking. Working with slopes of lines is a good thing to be able to do. And use it to your advantage to be able to graph the line. And then finally, we're going through this little review for graphing lines. We've also looked at these special cases. And remember, so if you have an equation like this one, x equals negative 3, then because the equation is in the form x equals k, you know that you have a vertical line. Right? And so you don't need to use any plotting points. You don't really need to use intercepts here. You can sketch the line pretty easily just based on the form. So you have x equals negative 3, goes through negative 3, 0, and you've got this graph like this. And there's x equals negative 3. So don't forget that x equals k, those kinds of equations are always vertical lines when you graph them. And then going along with that, y equals 4, right? Same kind of problem, except now this is y equals k, and we know that these are horizontal lines. right? When you see an equation in that form, you know you have a horizontal line as a graph. So looking at this graph, again, you need to be able to recognize that when you see it. And again, you're going to be a much stronger college algebra student if when you see x equals whatever, you know, hey, that's a vertical line. Or if you see y is equal to whatever, you know that that's a horizontal line. Be able to recognize those at the beginning of college algebra is a great thing to be able to do. So, and there's your graph, goes through the point 0,4, and you've got the graph. Okay, so I wanted to go back through and do a little bit of reviewing of graphing lines, because that's something that you're going to need when you're talking about graphing linear inequalities. So now let's flip the screen back for a minute. Remember, what we're talking about in this lecture today is we're not talking about linear equations. That's what we've just been reviewing for the last 10 minutes. But we're talking about linear inequalities. What happens when you have a less than or a greater than symbol in there? Okay, so that's our goal. So now let's look at just equations and inequalities in one variable for a few minutes. We need to do some reviewing for that idea. So let's look at equations and inequalities in one variable. Now, when you look at equations and inequalities in one variable, if you were graphing them, you don't graph them in the plane. You don't graph them on the XY coordinate system. You just graph them on a number line. All right, so if I graph the equation x equals 3, just in one variable, if we're thinking about that as an equation in one variable, that's pretty boring, right? This is the graph. Here's 0, 1, 2, 3 on a number line like that. And the graph of that equation would just be that dot right there, right? That would be the graph of the equation x equals 3 on a number line. You wouldn't have y equals, right? These equations would always be x equals. They'd always be just on a number line. Or you could write y equals if you wanted to, but it would still just be a graph on a number line. So x equals negative, let's say negative 5 halves. Right? You just have to make sure that you find where negative 5 halves is on the number line. Remember, write it as a mixed number if you need to. That's negative 2.5. And so I always like to locate 0 on here and try to kind of get a scale on the number line. So there's my number line right there. And then negative 2.5 is right about there. Right, and you've graphed that equation. That's x equals negative 5 halves on the number line. That's if you're thinking about it as an equation in one variable. No big deal. Now, what happens when we make the shift, though, when we look at inequalities in one variable? So let's look at x less than or equal to 3. X less than or equal to 3. All right, so if you've got x less than or equal to 3, so here's 0 on the number line, and you're thinking about what real numbers make that equation, or I'm sorry, that inequality true, and what you're saying is that any real number that's less than 3 or equal to 3 would make it true, right? So solutions are numbers that are to the left of 3 on the number line. And it's not just the dots at 0, 1, and 2, but it's all the numbers in between also, because it's any real number that's less than or equal to 3. And so what we would do is, and by the way, 3 would also be a solution. So 3 is a solution. So is 2 and negative 5 and negative 3/4 and negative 6.87, and all those numbers that are to the left of 3 on the number line are solutions to this equation. I'm sorry, this inequality. And so we put a solid dot on the 3. That solid dot means that 3 is included as part of the set, and we would shade everything to the left of 3 on the number line. So I'm going to shade it like that. I'm putting it in red there. And that would be the graph of that inequality, x less than or equal to 3. Now, what I want you to do here is start looking at the equation x equals 3 and the inequality x less than or equal to 3 and kind of compare those two. If you compare those two, so I'm going to put a green box around this one and a green box around this one. Notice that the equation is the dot, the inequality is the dot, and then everything shaded to one side of the dot. So the dot is kind of like the boundary to that solution, set, right? So the equation acts as the edge of the solution, right? The edge of that solution for x less than or equal to 3 is 3. That's the equation, x equals 3. And so that equals, if you replace the less than with an equal sign, you get the edge of the solution set, or the boundary to it. The textbook we use refers to it as a boundary to it, which makes sense to call it that. If you look at x equals negative 5 halves, if we look at x greater than negative 5 halves, on a number line, x greater than negative 5 halves. Now I want you to compare this one to the equation. So greater than, notice there's not a greater than or equal to, there's just a greater than. And so, first of all, negative 5 halves is not a solution to this inequality. So there's 0, there's negative 1, there's negative 2, there's negative 3, like that. So negative 2.5 is not a solution because it just says greater than. And so we put an open circle where the negative 5 halves would go. That open circle means negative 5 halves is not a solution. Negative 5 halves is not a solution in this case, and so we use an open circle. But any number that is greater than negative 5 halves would be a solution to that. And on the number line, those are all the numbers to the right of negative 5 halves. And so we would shade everything to the right in this case. And so one thing I want you to look at those two graphs and compare them. When I say those two graphs, I'm saying the equation and the inequality. So look at this one that I'm putting a red box around right here, and this one that I'm putting a red box around. Notice that again, the equation is the boundary for the solution set. And then what are you doing? You're plotting the boundary, and then you're just shading one side of the boundary, right? One side or the other. In this case, since it's a number line, it's to the left or to the right of the boundary like that. So if we flip the screen here, then if you look at the inequality x greater than or equal to 1, then based on what we've just seen on the last screen, the boundary for this graph would be the graph of x equals 1. Right, that would be the boundary to it. And so on our number line, if this is 0 right here, let's make the scale just a little bit bigger so we can see things. Right, we're talking about the boundary being x equals 1. Since it says greater than or equal to, 1 is a solution, so we put a solid dot. So notice the greater than or equal to will give you a solid dot. If it had just been greater than, then it would have been an open circle. So there's our boundary right there. And then what do? We shade one side of the boundary. And since it says x greater than, we shade to the right. And there's our solution set. There's the graph of the solution set to that inequality. It's 1 and everything to the right of 1. All right, and I want you to get the idea that, that if you're looking at an inequality, if you replace the inequality with an equal sign, then you're getting the boundary of the solution set. That's the edge of it. All right? So if we have x less than 5, x less than 5, then what would happen here? The boundary for this graph would be the graph of x equals 5. And again, there's the inequality, x greater or x less than 5. There's the boundary of that solution set, which is x equals 5. That would be the edge of it. And so here's 0, 1, 2, 3, 4, 5, 6. There's my number line. We're talking about x less than 5. So there'd be an open circle around the 5. That less than would give us that open circle right there. Means that 5 is not part of the solution set. And then which side of 5 do we shade? Which side of that boundary do we shade? Well, it says less than, and so we shade to the left in this case. And so the solution set would look like that. I put an arrow there, and that arrow just implies that it's everything to the left. You don't necessarily have to draw it all the way to the end there, as long as you draw it out that way. All right, now these are all equations and inequalities in just one variable. That's not really what we're talking about in the section, but you need to understand this first before you can go to equations and inequalities in two variables. So let's look at that now. And this is really our main topic for the day. So equations and inequalities in two variables. Now, it is exactly the same thing. The equation, just like we've seen on the last couple of examples, the equation is the boundary for the inequality. All right, so we're going to look at an example. To start off, we're going to look at several examples here. So let's say we have x plus y greater than or equal to 2. So notice this is a inequality in two variables. So now we're going on to two variable problems. So this is an inequality in two variables. So just like what we've seen with equations and inequalities in one variables, the equation, so if you take the order symbol, the greater than or equal to, and you replace it with an equal sign, this is the boundary of the solution set. And what kind of graph? And so when we graph this, all right, so let's do this correctly this time. And I apologize for that very careless mistake I made. So the x-intercept is going to be at 2, 0, and the y-intercept is going to be at 0, 2. And so our graph of the line looks like this. Let's see if I can get it right this time. So here's 2, 0, and here's 0, 2. And there's my line right there, the line going through those 2 points. Now, once again, because this is greater than or equal to, this means that the line is part of the solution. And if it's part of the solution, you make it a solid line. If it was just greater than or just less than, then it would not be part of the solution, and then it would be a dashed line or a dotted line. All right, so in our problem here, I'm going to make a solid line, and this is not the graph of the inequality. This is the graph of the line. This is the graph of the boundary of the solution set. So once again, the solution set is either going to be, right, in other words, you're saying that every point on one side of the line are solutions and every point on the other side of the line are not solutions, or vice versa. So in other words, you're either going to shade this side of the line, shade above the line, and you're saying that all of these are solutions, like that, or you're shading this side of the line like this, and you're saying that all of those points are solutions. And so you're trying to decide which side of the line to shade. All right, so what we're going to do is we're going to pick a point and test it and see if that point makes the inequality true or not. So we're going to use what we call a test point. So we use a test point and see if it makes x plus y greater than or equal to 2 true or false. If it makes it true, the test point that we use, then all the points on that side of the line are going to be solutions, and we shade that side of the line. If it makes it false, that means the other side of the line is going to be where all the solutions lie. Now, the test point I usually use when I can is 0, 0, because that makes the arithmetic as easy as you can make it. So the only time you can't use 0, 0 if it is actually on the line. So if I use 0, 0 in my inequality, and remember the inequality is x plus y greater than or equal to 2, so you have 0 plus 0 greater than or equal to 2, 0 greater than or equal to 2, and 0 greater than or equal to 2 is false. And so look where 0, 0 is. Here's 0, 0, and it's below the line right here. So what are we going to do? What are we saying here? That not only that point, but all the points on the same side of the line as 0, 0 make the inequality false. And that means every point on the other side of the line makes it true. And so that's what we do, is we shade the other side of the line. Because 0, 0, our test point, made it false, we shade the other side of the line from where 0, 0 was located. And those are the solutions. I've graphed the solutions for that inequality, x plus y greater than or equal to 2. Now, what you ought to do here, or what's not a bad idea to do, is to test a couple of points just to see if you're actually right or not. So pick a point. You don't have to do this certainly, but this certainly will give you some a good feeling that you're right here. If you pick a point, like in this case, this is 2, 3, and you test 2, 3 in the inequality x plus y greater than or equal to 2. So you get 2 plus 3 greater than or equal to 2, which is true. 5 is greater than or equal to 2. So that gives you a good idea that you're on the right track here. If you used a point on the other side of the line, like that point right there is negative 3, it's 3, negative 2. That's 3, negative 2. And if you use that in the inequality, x plus y greater than or equal to 2, you get 3 plus negative 2 greater than or equal to 2, and you get 1 greater than or equal to 2, which is false. And so notice that point, this point made it true, this point made it false. 0, 0 we saw made it false. So notice all the points on one side of the line will make it false. All the points on the other side of the line will make it true. All right? So what are our steps? Okay, so that's our kind of introductory example. In the next example, we'll try to go through and not make any careless errors. Okay, so on our next example, we have 2x minus 3y is less than 5, we'll say. 2x minus 3y is less than 5. All right, so what we could do here is we could, again, use intercepts. What do we know that the boundary of this solution set is? The boundary would be the equation 2x minus 3y equals 5. Remember, all you do is take the order symbol and replace it with an equal sign, and you get the boundary. Right? And would the graph be solid or dashed? Because the order symbol in this case is less than, this is going to be a dashed line. Right? Be thinking about whether it's dashed or solid. By far and away, the most common mistake I see on the exam on this kind of problem is failing to put either a solid or a dashed line correctly. And in fact, almost everybody just puts a solid line and never even thinks about dashed lines there. Remember, that dashed line means that the line is not part of the solution set. So in this case, the line has to be dashed because it says just less than, not less than or equal to. All right, so let's graph this line. And because of the way the equation's written, I'll probably just use intercepts. Seems to be the most, the easiest or the most efficient way. Put 0 in for y and 0 in for x. So I put in 0 for y, and I get 2x equals 5, or x equals 5 halves. So this is 5 halves 0 right here. And then the y-intercept, I put in 0 for x, and I get negative 3y equals 5. So that's y equals negative 5/3, like so. And so when we go over here to graph this, here's my coordinate system. 5 halves 0, that's 2.5 0. And remember, we're not going to include the line. Sometimes you'll see books plot 5 halves 0, but actually put an open circle there. If you put an open circle or a dot, I'm not going to care as long as you put the dashed line there. And then 0, negative 5/3. Let's see if we can put this in the right place this time. That's 0. So by the way, this is 5 halves 0 is 2 1/2 0. And 0, negative 5/3 is 0 and negative 1 2/3. All right, so you've got negative 1 2/3 is like right about here, and there's the y-intercept. And then we make this a dashed line in this case. And you're making this a dashed line because you're saying that that line is not actually part of the solution set. All right, so now the next question. So we've got the boundary graphed. And so the boundary is always just going to be a line. And then the next question is which side to shade. Right? And so what do? I'm going to test 0, 0 in our problem. Test 0, 0. And remember, you test it in the inequality. So this is 2 times 0 minus 3 times 0 is less than 5. And so you get, that's all 0, so you get 0 less than 5. And 0, 0 in this case, notice, makes this inequality true. Here's 0, 0 right here. And that's going to make it true. And so since that made it true, that means 0, 0 is on the correct side of the line. And so that's the side we shade. If it had made it false, then we would have shaded the other side of the line. All the solutions lie over here. And so this is the solution set for this inequality. It's all of those points like that. And notice the boundary itself is not part of the solution set. If you're really concerned about this, then plot a couple more points just to kind of get an idea of whether you're right or wrong. So, take a point on both sides of the line and make sure that, that actually makes it true and false like it's supposed to. So here's the point, negative 1, 3. Negative 1, 3 is in the shaded region. It should make this inequality true. Right? So what do I have? I have 2 times negative 1. Right? You have negative 1, 3. So 2 times negative 1 minus 3 times 3 less than 5. So you have negative 2 minus 9 less than 5. Negative 11 is less than 5. Certainly that's true. And then if you use a point to the other side of the line, so let's say I use that point right there, which is 4, negative 2. Right? If I use 4, negative 2, I put 4 in for x, negative 2 in for y, and I get 8 plus 6 less than 5. I get 14 less than 5, and that's definitely false, right? And which it's supposed to be, right? It's in the non-shaded part of the line, and so, or non-shaded side of the line, and so clearly should not be a solution to that inequality. All right, so I think we're doing good here. Hopefully there's no questions so far. Let's look at a couple more examples, and really after we get through a couple more examples, then we're going to be finished up with what we're going to do today in class. So next problem I want to look at, let's look at, and by the way, one thing I didn't mention on the last problem, notice you can't go by the direction that the order symbol is pointing as to which side you shade, because a lot of people will look at 2x minus 3y less than 5, and they see the less than at the beginning, and they go, well, if it's less than, it must mean I shade below the line. But notice in this case, what do? We shaded above the line. So it depends on the form that the inequality is written in and the signs and things like that. And so you can't base it on the direction that the order symbol is pointing as to whether you shade above the line or below the line. Okay, so you've got to use a test point. All right, so let's say we have y is greater than negative 2/3 x plus 1. All right, y equals y greater than negative 2/3 x plus 1. All right, so the boundary, always kind of write this down first. The boundary to this solution is y equals negative 2/3 x plus 1. And so the form for that inequality is that the slope is negative 2/3 and the y-intercept is 0, 1. And so I think that's the easiest way to graph this line, is just to use the slope and the y-intercept. That's what I'm going to do right here. And by the way, the boundary in this case is going to be dashed again, because this is just greater than, and it's not greater than or equal to. So since that's a greater than, this is going to be a dashed line. All right, the slope is negative 2/3, and so remember, one way to do that is to use negative 2 over 3, or use 2 over negative 3, either way, for the slope. Let's see, so the y-intercepts here at 0, 1, and then the rise over the run is negative 2 over 3, and so that means go down 2, there's my rise, and then run 3, go to the right 3, there's my run, and that's another point on the line right there. And so I'll make that one an open circle also, and there's my line right there. Right, so like so. Right, so that's the boundary to the solution set. And so now the next thing I'm going to do is I'm going to test 0, 0 in my inequality. And I'm going to see if it makes it a true statement or a false statement. So here's my inequality. I'm putting 0 in for y and 0 in for x. And so I get 0 greater than 1. And 0 is not greater than 1, right? 0 is less than 1. So this is false. And because it's false, and look where 0, 0 is. 0, 0 is located right here. There's my origin. It's below the line in this case. So that means I shade the opposite side to shade the solution set. That means all of these points over here are solutions to the inequality, right? And all the points on the other side are not solutions to the inequality. All right, so hopefully I'm not getting any questions yet, so hopefully we are doing okay. Hopefully we're doing okay. I don't see any questions at all. So we have just a couple more examples, and then we're going to be finished up. All right, so next problem. 2x minus y is less than or equal to 0. 2x minus y is less than or equal to 0. All right, so when we're looking at this, the type of inequality, first thing we do is we write down the equation for the boundary, right? We replace the order symbol with an equal sign. That's our boundary. This line will be solid because this is less than or equal to. So this means we're going to have a solid line. And remember, this is one of those lines, you have 2x minus y equals 0 that actually passes through 0, 0. Because there's a 0 over there on the right side. So this actually goes through 0, 0. And so what I'm going to do to graph this line is I'm going to put it in slope-intercept form. I'm going to subtract 2x, and then multiply or divide both sides by -1, and I get y equals 2x. So the slope of this line is 2, which is 2 over 1. So looking at the graph here, right, what do we have a line that goes through 0, 0, goes through the origin, and then the slope of this line is 2. Rise over the run. So this goes up 2 and over 1. And we get another point on the line. And so here's my line, and remember, we're going to make this line solid because this is a less than or equal to. That means the line is actually part of the solution set here. Now notice that this line actually passes through 0, 0. So my test point, if I'm going to use a test point here, so the test point cannot be 0, 0 since 0, 0 is on the line. It would not tell you which side to shade. And so we need to test another point. So we test another point. And so it doesn't matter what you pick. As long as you are pretty clear that it is not on the line, you're going to be okay. So like I might pick 3, 0. 3, 0 on my picture here is pretty clearly not on the line, right? There's 3, 0 right there. And so I can test that point, and I can see if this makes this a true statement or not, this inequality a true statement. So you have 2x minus y less than or equal to 0. So that's 2 times 3 minus 0 is less than or equal to 0. And it gives you 6 less than or equal to 0, which is false, right? 6 is greater than 0, not less than or equal to 0. And so this point made the inequality false. So that means every point on the same side of the line as that point makes it false. And it means every point on the other side has got to make it true. And so here are all my solutions in this inequality, all of these points over here. All right, so there's my solution set for this particular inequality. And again, you could pick some points in the plane and test them and make sure that they either make it true like they're supposed to or make it false like they're supposed to, based on where they are. All right. A couple of kind of special cases here. So let's look at this inequality. X in two variables, x less than or equal to 2. There's only one variable in there, but remember, we can treat these as inequalities in 2 variables. So you don't do anything different here. You look at the boundary, which is x equals 2. That would be a solid boundary because it's less than or equal to. Now, what kind of a line is x equals 2? Right? X equals 2 is in the form x equals k. That is a vertical line. And so remember, you don't have to do any special forms. You don't have to plot points. You just use what you know about vertical lines. And so you know you have a vertical line that goes through 2, 0. And so here's our boundary. Goes through 2, 0. It's a solid boundary, and so we would make this a solid line like this. And there's the equation x equals 2. All right, so here's x equals 2 right there. Make sure we distinguish it. There's the y-axis, there's the x-axis, like that. All right, now we decide, we test, you can test 0, 0. I mean, it should be pretty clear which side to shade since it says x less than or equal to 2. But if you want to, you can certainly just go through and test 0, 0 and see if it makes it true or false. Now, x less than or equal to 2, there is no y in there, so you don't have to worry about substituting for y. You just substitute for x, and you put 0. And 0 is less than or equal to 2. That's true. And so here's our origin. That makes it true. That point makes it true. And so that means every point on the same side of the line makes it true. And so we shade everything to the left of x equals 2. This is going to be our solution set. It will be all of these points over here. And it made sense in this case with a vertical line that you'd get x less than or equal to 2. You'd get everything to the left of that line like that. Those would all be x values less than 2. All right, we are just about finished. One last problem here, and we are done. So let's look at y greater than or equal to, greater than -3. Y greater than -3. So in this case, I think you know how this is going to go based on the last problem. The boundary is the equation y equals -3. That would be a dashed line because this says strictly greater than right here. It's not equal to. And y equals -3, we know, is a horizontal line because any equation in the form y equals k has a graph that's a horizontal line. And so here's our horizontal line like this. Here's our coordinate system. There's the x-axis and the y-axis. And you've got the line y equals -3, which is that horizontal line through 0, -3 right here. We make it a dashed line, and so here's our boundary right here. All right, the y-axis kind of continues down like this. There's our boundary, and that's the line y equals -3 like that. We could pick a test point, which is 0, 0. If we want to do that, that's fine. I think you know which side you're going to shade here because it says greater than -3, but we could test 0, 0. Here's our inequality, y greater than -3. We put in 0 for y, and 0 is greater than -3. That is a true statement. And so we shade everything over here. Right, 0, 0 made it true, so we shade everything above the line, like that. And here is 0, 0 right here, and that's y, because that point made it true right there. All right, so you've got a good little introduction to graphing linear inequalities. This is actually, believe it or not, there's business applications where this is starting to lay the groundworks for some things in business applications. In something called linear programming, where being able to graph inequalities like this is important to be able to do when you're trying to find optimal solutions to various kinds of problems. So this is something that will lay the groundworks for that for those of you who are going into a business set of classes upcoming after intermediate algebra. All right, so a couple of things just to mention here. So you've got textbook homework. I will continue to assign this. I don't know how many of you are doing the textbook homework since I don't pick it up, but these are good review problems to look at, and so I think it always gives good practice. And this is on page 544 of your textbook, and I would start it on problem 511, and I would work through probably 549. The odds, and I would just work as many of those problems as you can. On WebAssign, you need to, you're going to be graphing some of these things on WebAssign, and so you need to pay attention to the directions that come up on the screen as far as walking through how to graph an inequality in WebAssign. So I want to kind of point that out. It does give you the option to shade one side or the other. It gives you the option of whether to make the line a dashed line or a solid line. And it gives you the option of plotting some points and then actually dragging a tool through those points to sketch the line itself. So you do have all the things we're doing on paper you can do on the screen there. You just have to kind of be patient, walk yourself through it. Once you get through an example or two on the screen, then it's not going to be hard to do. Remember that the factoring contest is tomorrow, and I know some of you can't make it strictly because you work, and unfortunately there's just nothing I can do about that. It's scheduled at 3:30. They just have to base it on the best time that they can, which is kind of between the day classes and the night classes. So it's 3:30 in Winship 207. You don't need to register ahead of time or anything like that. And it is November the 15th, which is tomorrow. There is a review on your website or on the Google site for the class, and so you could go to that and do a little bit of reviewing of factoring, which would not be a bad thing if you want to prepare for that contest. Anybody have any questions?
I'm good.
No.
Okay, then everybody have a wonderful day. Please stop by if you have during my online office hours if you have questions. We will start talking about functions on Thursday, so that's a very important lecture to finish up the semester. And we only have 3 lectures left. We only have 3 homework assignments and WebAssign left after this linear inequality stuff. So we're just about done with the semester. We're rapidly finishing up. So have a great day. Please stay in touch with me if you have any questions, and I'll talk to you soon. Oh, let me stop the